So let's look at an example of an application of the equation we just derived. So to recall, we derived the equilibrium frequency for a deleterious allele as being mutation rate divided by SH. And the example we'll be looking at is for a genetic disorder called chondrodystrophic dwarfism. So this is one of the forms of dwarfism where long bones don't develop properly. So chondrodystrophic dwarfism is a dominant genetic disorder. And so what does dominant mean? If you think about in terms of these values, dominant meant that H was equal to 1, right? Having a single copy reduces fitness as much as having two copies. So we have fitnesses that we're going to represent. Remember, these were as so. And the H of 1 means that this individual here, the heterozygous individual, has the reduced fitness of a homozygous individual because it's dominant. So if we want to use this equation, we want to think about what sort of question might we have. And the question that this genetic disorder will allow us to address is, what is the mutation rate from functional alleles for bone growth into ones that cause dystrophic dwarfism? And that's actually a really difficult question to study from a genetic point of view, because since mutations themselves are so infrequent and so rare, if you looked at a population, you hardly ever see one happening de novo or brand new. But we can use this equation to infer what the historic mutation rate would have been in order to lead to some sort of equilibrium frequency like we see now if we just had S and H, right? If we had S and H and Q, we could solve for mu. So what are S and H and Q? Well, H is 1 because it's dominant. So now we just need Q and S. So what's our best guess at what the value of the equilibrium frequency is? Well, we can go and look at modern society and see what the frequency is. And so if we go, and this was a particular study that did this, they looked at 94,000 births in hospitals. And of those births, they were able to identify that 10 of them were chondrodystrophic dwarf individuals. So of this many people, babies, 10 had this genetic disorder, and these 10 individuals were almost definitely heterozygous, right? When alleles are at very low frequency, they're almost always present only in heterozygotes. So if we think about what is the allele frequency of that, well, it's 10 alleles out of 94,075 individuals times their 2 alleles each. So that gives us a value of about 5.3 times 10 to the minus 5 for the allele frequency of the deleterious allele, so that's Q. Now to measure S, the fitness consequence of this allele, the best guess we can do is go to look at modern individuals and how many offspring do they have. And so if we look at 108 dwarf individuals that were examined, they produced 27 offspring. And then this study looked at 457 of their siblings. So these are individuals that are genetically very similar to them, except they don't have the dwarfism allele. So they're genetically similar, and they're culturally similar, and economically similar, and religious similar, etc. And those 457 individuals had a total of 582 kids. So these dwarfs, on average, are having 27 divided by 108 offspring each, so that's about 0.25 each. Their siblings, having 582 divided by 457, they're having on average 1.25 offspring each. These numbers are slightly rounded. When I use the full numbers, the fitness of a dwarf, 1.27, it's actually a 1.27. The fitness of a dwarf individual relative to their unaffected siblings, or their siblings that don't have the dwarfism allele, is 0.197, so about 20%. So this is a real deleterious allele, right? Individuals with this allele have 20% the offspring of their close relatives that don't have that allele. So what's the actual value of S? 1 minus S here is what matches up with this actual fitness value here. And then solving for S, we get S of 0.803. So now we have a value of Q, which is our equilibrium. We have a value of S, 0.803. And we have a value of H. So we have this, this, and this. We can solve for the mutation rate. So starting with this, solving for the mutation rate would be this. So plugging those numbers in, 5.3 times 10 to the minus 5, 0.803, 1. When you plug all those in, 4.256 times 10 to the minus 5 for a mutation rate. So this means this mutation happens 4 times out of every, say, 10,000. So that's a very rare thing. You would not see that if you just looked at individuals who weren't dwarves and how often do they produce offspring that are dwarves. Very, very rarely, but we can use this technique to solve for that mutation rate, something that's otherwise very difficult to measure. So one of the applications of this mutation selection balance equation that we have derived is it allows us to estimate genetic mutation rates, which is something that's of great interest both to evolutionary biologists and to regular geneticists. Now, one thing to note about this equation here is that it actually would fail when h is equal to 0, right? Because you can't divide by 0, that's illegal or something. When h is equal to 0, that's the situation here where this fitness is 1 and this reduced fitness is only experienced by homozygotes. H equals 0 is when the deleterious alleles are recessive. So this equation that we've derived, although it works for dominant deleterious alleles, does not work for deleterious recessive alleles, right? Ones in which the fitnesses would be 1, 1, 1 minus S. And as I mentioned before, most of the genetic diseases that we have in society, in fact, most of the deleterious alleles that we have knowledge of are in fact recessive alleles. So there's a different equation that we get if we do a different derivation, and this is actually one of your homework questions, is to redo the derivation from previously and actually prove that the equilibrium frequency that you would get for deleterious recessive mutations is of this form. Now, when you're doing this derivation, the derivation that I did, we eliminated some terms because they were approximately 0, and I said p was approximately 1, and I made those sorts of approximations throughout the derivation. The derivation for your homework assignment, you do not have to make any sorts of approximations like that. This is actually an easier derivation than the one that I did, and you kind of know what you're headed towards. So start that derivation off the same way as the previous one that led to this equation started. You don't need to make any of these approximations, and you should be able to derive this equation, which is the appropriate equation to use for deleterious recessive alleles.